enthalpy is a state function. What's the other state function that we've talked about? Starts with an E. Haven't gotten to entropy yet. Energy, right? Internal energy. Okay, good. Just double checking. All right, so those are our two state functions. That doesn't matter how we get to the final state. It's just going to be final mass initial. So, since they're state functions, it means we can add, subtract, multiply, divide individual enthalpies or internal energies. So we can add, subtract, divide. We can do math with individual enthalpies to get the overall enthalpy. There are a few rules to the math we use with enthalpy, which is, if you have your PowerPoint, they're all laid out here. We're going to walk through them and then do some examples. So, the stoichiometric coefficients always refer to the number of moles of a substance. That's just a general true statement, right? The big number in front of, if I had two H2Os, it'd be 2 moles or 2 molecules. It's referring to that. So in this case, I have water in its solid state going to water in its liquid state. The enthalpy of that reaction is about 6 kilojoules. If I want to know about the enthalpy of the reverse reaction of water freezing, it is the same value but opposite sign. That makes sense, right? It's the same amount of energy, final mass initial. For it's 6, reverse it's minus 6. If I double the molecules of water, I also have to double the enthalpy. Because really, right, we were saying that this is per mole. It's not always written per mole. So if I double the number of moles, I have to double the enthalpy. And as you're looking up, as you've looked at probably in lab this week, when you looked at Appendix 2 in the back of your book, there is a ridiculous number of options for oxygen and water. And it's very important that you choose the right one for the right state of matter. That's all it's saying. That solid to liquid is 6 kilojoules, but liquid to gas is 44 kilojoules. So when we do these, it's very important when you're using the table to make sure you're using the right state of matter in each one. All right, so then let's take a look at how we can use these. Let's say, actually, I'm going to do an easier problem first. We'll work up to that one. I decided I didn't have enough practice problems in this chapter, so we'll do one in here. So, if a reaction is a series of steps, then the delta H total is going to be the sum of all the individual steps with individual delta H reactions. So, let's say this is going to become a big problem. So if you're spacing yourself out, you might want to use the back of a page or a separate sheet of paper. Alright, so I want to find the delta H reaction for 3 carbons plus 4 hydrogens goes to 1 C3H8, 1 propane. know that step. I know that if I add the propane and oxygen, I can get carbon dioxide and water. And what is that negative sign telling me about the delta H? Which way is the heat flowing? It's exothermic and it's flowing out to the surroundings. Out to the surroundings. Good. Okay, I could take carbon and oxygen and combine them to make carbon dioxide, which that has the delta H of negative 394 kilojoules. And finally, I can combine hydrogen and water to make gas, or hydrogen and oxygen to make water, which has its delta H. So the question is, how can I use these to get to the reaction I want? So I can add, subtract, multiply, divide all the delta H's. You can do it in a variety of ways. There's a bunch of different methods which all work equally well. I like to start with what I know the product is. So, which of the reactions contains the products? The first one, the second one, or third one? First one. Okay, is it in the right direction? No, not in the right direction. So what I need to do? Flip it over. Okay, so if I flip that, all right, so if I flipped it over, what happens to the delta H for this? All right, change the sign. Does it change the value? No, common mistake. Don't change the value. Does it have the right stoichiometric coefficient for the C3H8 for what I want? Right, I want one, I have one. Good. So now let's look at my second reaction step. Is the carbon solid on the right side of the equation? Is it the right stoichiometric value? What do I need to do to that? Okay. So I have now 3 carbons, 3 oxygens, and 3 carbon dioxides. So now what happens to the delta H? Does it change sign? Just changes value, right? Now it becomes 3 times as much. Oh, if you don't have your calculator out, go ahead and fish that out because we're going to be doing some calculations today. Because if everybody find it. As we know for Monday, my calculations have been a little bit rough lately. So I definitely need someone to double check them. That's it. I'm going to wrap up my calculator. Alright, last step. Done that one, that one, that one. Alright, so now I have the hydrogen. What do I need to do to equation number 3 to use it in the top? Multiply by 2. Okay. Alright, here comes the moment of truth. Before you do any calculations, you have to cancel out similar quantities on both sides of the arrows to make sure you actually made what you thought you wanted to make. Does that make sense? So, over here I have 3 carbon dioxides. Are there 3 carbon dioxides to be found on the product side? Yes. So I can cancel both those out. Okay, what about water? Do I have 4 water on the product side? Okay, I can cancel those out. see, I want 3 carbons. Okay. The last thing is I have 5 oxygens as a product. Do I have 5 oxygens on the other side? I do. It's a little trickier to see. That cancels out with both those. So then you write what you have left. Forgot my statement there. Is this the equation that we want to make? Good. So then the last step is to sum up all those delta H's. Everybody got something in that ballpark? 107? Good. Now let's think, does this make sense? I have carbon and hydrogen combining to make a negative exothermic. That should intuitively hopefully make sense, that we are making something and releasing energy. I mean, based on all this, you should see that it should be negative. So we'll work on some more problems where you can kind of fine-tune your intuition on these kind of problems. All right, let's do another one. It's the one that's in your PowerPoint. This one has some funkier states of matter. All right. I want to make this as my final reaction. Graphite and rhombic sulfur make sulfur carbon disulfide. These are my equations I can use to get to the end. Why don't you guys work in your little groups, move things around, just because I feel like everybody should get up. Why don't you guys move to your quiz-taking groups, and we'll do this problem, and then we'll do a few more problems. There, I can work on my next one. I don't think I have that written down. So go ahead and start working on this one, and I'll put up one more of a similar style. Yeah, a few people agreeing. Some flipping, reversing, multiplying. These are just like puzzles. It's very hard for me to teach you how to do a puzzle, right? You just have to kind of keep doing it until you can see, oh, I need to flip that. Oh, I really need 2 of these, so I'm going to multiply by 2. Kind of like balancing equations. You're going to just practice a little bit with your group. All right, here's my challenge problem. This will take probably several attempts between you and your group to get it right. So I want N2O plus NO2 makes 3 nitric oxides. And I've given you 3 equations to try and make your way there. Yes. Sorry. Those are all G's. Sorry, that shouldn't be the tricky part. No. I forgot my gaseous state in the very top row. That's not the tricky part. Tricky part is really you'll do this part. You'll do it in 2 parts. There's a problem like this that I'm mastering, so I'm trying to get everybody up to speed.
Alright, let's start looking through this all together. I need a reaction that has N2O as a reactant. Which equation should I use that has N2O as a reactant? Reaction 1, 2, or 3? Use 3. Do I use it as is or do I flip it over? As is, alright. Okay, now I need the reaction that has NO2 as reactant. Which equation can I use that has NO2 as a reactant? 1, 2, or 3? 1, then what do I have to do to it? Flip it over, okay. Okay, so I've used equation 1 and 3. So this one has nitric oxide as a product. So I'll use that one as is. Because I need to get to 3, and right now I can't figure out a way to get to 3, right? Because I'm at 2. So that takes 2 steps. So let's take a look and see what I can cancel out. Oh, did I skip a step? I did. I skipped a step. Hold on. This one should be I2. Yep, this one should be I2. There we go. So, 2 N2s, 2 O2s. 4 NOs. Okay, good. Alright, so now what is something I can cancel out that's on both the reactant and product side? N2? I got 2 of them here and 2 of them there. What's the other thing? The O2s can cancel. Alright, so if I cancel those, my new equation is this. Everyone agree with that so far? Did everyone get at least that far, hopefully? Is it that far? Yeah. You could have used half ratios. Am I where I want to be? Is this the final reaction I actually want? No, because I wanted 1, 1 to 3. I'm at 2, 2 to 6. How do I get from where I'm at to over here? Divide by 2. If I divide by 2, what do I do to my delta H? Divide by 2 also. You could have used half ratios. You could have done 3 halves amongst here to try and get the 2s and the 3s to cancel out. I think it's a little bit easier. Is that not half? 315 divided by 2. I got it. Oh, did I mess up my math a step above? That would be why. That would be why. Well, that's why everyone should have their calculator out, because there's a good chance I messed it up. Negative 1, 6. Lost a decimal point on my calculator. Happens. Is that better now? Anyone bother double check me again? No. Alright. Let's see if no one says anything unless you're right this time. Alright. Questions on how to do these kinds of problems. Flip it, multiply it, divide it, rearrange it. Alright. In that case, let's do the last topic in chapter 6, which is enthalpies of formation, and using them with Hess's law. So, standard enthalpy of formation is the heat change that results when 1 mole of a compound is formed from its elements at a pressure of 1 atmosphere. That's a lot of definition, but you just need to know that delta H with the 0 is different than delta H reaction, or some of the other delta H's we're going to run into. What's really the most important thing, I'll probably ask you about later, is that the standard enthalpy of formation of any element in its most stable form, which means the way it's found in nature, is going to be 0. They decided to set their scale that way, that formation of an element is 0, then formation of a compound from an element would have a different value. So that should make sense. So, right, oxygen should be 0, and graphite should be 0. Diamond is pretty close to 0. Ozone, definitely not 0, because you gotta do something to the oxygen to make ozone. So, how we use enthalpies of formation. Is in this kind of way. So I think this is also from Mastering Tonight. Write an equation for the formation of glucose from its elements. We know the heat of formation is negative 1,273.3 kilojoules. This piece of information is not super relevant, so I don't know why they threw it in there on Mastering. They just really want you to write an equation that uses the elements in their standard state. So, what Mastering is looking for right, so carbons plus oxygens plus hydrogens. And then they want you to balance it. How many carbons do I need here? I need 6. Then how many hydrogen gases? Then how many oxygens? That's all Mastering's looking for. Just want you to recognize that elements make compounds, and that's where the delta H formation comes from. It's like part A, like a several part question. Apparently that was very confusing to some people last year, so that's what they want. How we're going to use these is for an overall reaction. So, to calculate delta H for reaction in the standard state, here is the fancy paragraph to explain what I'm going to write in math words. The overall standard state heat of reaction is equal to, what's the big epsilon? Sum, right? We're going to sum all the heats of formations of the products, each multiplied by their stoichiometric coefficient. So that's what the N is referring to. This so sum up all the heats of formation of the products, each multiplied by their stoichiometric coefficient. Subtract that from the stoichiometric coefficients times the heats of formation of all the reactants. So it's products minus reactants multiplied by their stoichiometric coefficients. is very confusing. It'll be much easier when we do this practice problem in about 5 seconds to see how we actually do it. But that's what we're going for. The overall heat of a reaction or heat of formation, depending on what the question is asking for. Which is what you guys did this week in lab when they asked about Hess's law. If you've had lab, the pre-lab, they asked about Hess's law. This is another way of writing it out. The overall heat of reaction. If this is my reaction, A, B, B, C, C, C. C times the heat of formation of C plus D, heat of formation of D, minus A, heat of formation of A, plus B, heat of formation of B. So Hess's law just says, use this equation. So when I say use Hess's law to solve, it means use this equation. So let's do some. Benzene burns in air to produce carbon dioxide in liquid water. I would like to know how much heat is released per mole of benzene combusted. So what we're going to need to do is use our Hess's law to solve this problem. Here's your equation, and there's your fancy table. So I'm looking for Alright, so we're just looking to plug it into this equation. So these problems are kind of long in terms of length to the side, so you may have to write tiny. So, what is one of our products? CO2. How many CO2s are in my equation? 12. So I'm going to do 12 times the heat of formation of carbon dioxide, right here. I'm going to leave off the units for now just because I don't have a lot of space. But keep in mind that it's kilojoules per mole. Okay, what's the other product? Water, right? And I have 6 waters. And water is right here. Negative 187.6. Do I have any other products? Those are it. So I can end my bracket. I'm going to subtract from that my reactants. So I have 2 benzenes. And I have 15 oxygens. You obviously don't have to include the oxygen because it's 0, but I like to always include it just to make sure I've accounted for everybody, just to make sure I haven't left any molecules out. Now, everyone's going to do some math. I'm going to do some math. We're going to hopefully end up with the same math. Has not been good so far today. Good? Okay, good. Alright, we're in kilojoules per mole for the written reaction. The question asked me, though, how much heat is released per mole of benzene? moles of benzene did I blow up in this equation? Right, 2. I blew up 2 moles of benzene, which means this value is really 2 moles benzene. Again, another tricky question I can catch you on. So how do I get per mole of 1 benzene? Divided by 2. Alright, want to do one more? Last thing in class today, before I send you off some announcements. Alright. Alright, so here's my equation. There's my really fancy table of values that, if they're not provided, they're in Appendix 2 of that yearbook. Alright, so what is considered a product in this? I heard this. Alright, iron. Got 2 nothing. Space. So imagine it's all in the same one. Can I get something like that? If it's negative, is that exothermic or endothermic? Okay, and which way is the heat flowing then? Not to the surroundings. Okay, we do a lot of exothermic problems.